missing lecture slides from the previous lectures. So I believe we should be up to date with that. Okay. So are there any questions relating to, I don't know, topics or organizational aspects of the lecture? All right. I don't hear anything. So then let's just go to our fundamentals of telecommunication lecture. Now, can you? Sorry. Now, can you see the slide correctly? I mean, correctly in the full screen mode, and can you hear me?
No, it's not full screen mode. We can see everything.
Right. Okay. Let's do it the usual. Just give me a second. All right. Now it's better, right? Presumably.
Yes, yeah.
Okay, brilliant. Right, so as usual, just a quick recap of what we've been talking last week. So we started the topic of optical fibers, and basically the core principle of how the optical fiber works. It basically uses the principle of total internal reflection, right? So basically, if we have a discontinuity between two optically transparent mediums, so by discontinuity we simply mean the two materials with different refraction index, and at a certain angle, because of the Snell's law, there will be, normally there will be refraction, of course, of the wave entering into the second medium. However, if we illuminate the boundary between the two at a certain angle, then at some point the refractive angle will be 90 degrees, which basically means that there will be total internal reflections, or to put it more plainly, that the wave will be like a sliding along the boundary between the two materials, if you can imagine. And directly from the Snell's law, which says that the sign of the incoming angle multiplied by the refractive index need to be the same as the refractive index 2, and the sign of the angle of the penetrating wave into the second medium. Directly from that, we can actually create the requirements for what to do with the optical fiber. And what's also important that here the requirement is not only in the material. So of course we need to engineer N1 and N2, but also we need to inject the beams of the laser at a certain angle into the optical fiber. Okay, then we discussed in general the concept about modes, and so again we talked about that in the context of optical fibers. However, a point I wanted to make is that modes is a very generic concept in pretty much any case when we deal with electromagnetic fields or Maxwell equations in any region that is basically bounded by something. So we will see similar modes in the cables or in the wires, in the waveguides. I'm sorry, not similar, of course. They will look different, but they will still the principle basically will be the same. So basically, to put it more plainly, is when we have the generic Maxwell equations, which are very generic basically, and we have an area or a volume with imposed some boundary condition, which is exactly the case in the optical fiber, right? When we got the boundary between the two material, the core and the outer layer, then it turns out there is a discrete number of possible solutions to the Maxwell equations, meaning, discrete number of basically the shape or the electric fields that can be supported by such a structure. Okay, and basically by discrete, we should keep in mind that the number is still infinite of the modes in the general case. However, it's discrete, and this is exactly what we see here for the 12 lowest modes of the optical fibers. And the reason why it matters is also because we can have so-called monomode optical fibers, which would support only the first one, the basic mode of the optical fiber. Okay, and then we talk about chromatic dispersion. So basically the idea is that not everything, so if we have a very short pulse, so short in time domain, as you should know, this typically means that it needs to consist of multiple frequencies, right? However, the problem is that in many optical fibers, there will be slight differences between the propagation speed of different frequencies, and this got to do with well, simply with manufacturing issues. So it's very challenging to have same refractive index, over very long cable, also over very wide frequency. And even though this changes in the refractive index between frequencies may be small, if you think about the of fibers running for tens of kilometers or even longer, this effect will accumulate. And since part of your pulse basically will be faster than some other part of the pulse, to put it plainly, which basically results in pulse spreading, so that the resultant pulse is will be longer than the in time than the initial pulse that you injected into the system. And this needs to be, of course, accounted for, simply because if you're transmitting train of multiple pulses, and at the input you might have sufficient separate to distinguish between them for the modulation. Even if that's the case, at the output they might merge with one into another and cause some problems with the modulation. Okay. And similarly to the chromatic dispersion, which is based on the frequency, we can see similar effect with what's called modal dispersion. So this basically means that different modes also may travel at different speeds. And this might be even more challenging, because over here we have two signals which have the same frequency, and just by the fact that they propagate with different modes, they will arrive at different speed, again stretching our pulse, right? Even if we use even if they are the same frequency. So basically, how this can be best imagined is when we talk about the skew rays in optical fiber and meridian rays within optical fiber, right? And you can realize that apparently the meridian waves, which travel just in the meridian or in the center plane of the optical fiber, will travel shortest distance than the ray which skews from the optical fiber at the angle. Okay, and just because of that, there might be some delays. Again, because of the length doesn't need to be huge per unit, but it will accumulate over long distance of the optical fiber. So that has to be taken into account. Finally, we talk about core network and access networks. So this is quite more on the system level, really. This is interesting distinction that you should be aware of. Simply that the core network, they basically handle large amount of traffic between huge computing centers. So basically there'll be like a lot of long distance point-to-point links. Every link carrying high capacity, high amounts of data. Whereas access networks, this is basically what you see as the user most of the cases. So those networks would be branching into multiple different ways or nodes. And at the end of the day, of course, the overall networks will carry similar traffic as the access networks. However, the individual link will be less capacity hungry, so to speak, right? So basically the idea is to more about branching and reaching out to all the users or all the devices that you want to connect to your network. Okay, so far so good. So do you have any questions about the optical fibers or the core or access networks that we discussed? All right, so now we move on to the wired media. So basically good old-fashioned cables or wires. And well, this might seem maybe less interesting topic than the optical ones, but still I hope I will be able to convince you that there are some interesting aspects of wired cables, especially if we use them at a millimeter wave or higher frequencies. And well, at the end of the day, in many cases, the cables still cover so-called the last mile problem, right? So basically, many buildings, many institutions, they will still to some degree rely on copper wiring for the last part of access network. Okay, so basically. Just to remind, what I would like to focus on in this lecture is not necessarily cable as such, but basically the electromagnetic fields around the cable, what happens around that, and what are the consequences. So, well, there are three different types of cables used in telecommunication. So that's a twisted pair or alternative multiple pairs. We can have a coaxial cable and the parallel lines. So parallel line might also include some forms of the PCB circuits that you use in your electronics. Okay, so this is just like a brief mention of the most simple case. So we have a twisted pair of two cables, and basically, the name says it's also two cables wrapped around each other. One carries the positive charge, the other negative charge, and basically the electric fields builds between the two cables. However, in this context, what's important that the two cables are not really bounded by any metallic conductor, right? So basically they would generate and accept quite a lot of interference, right? Simply because there's no shielding. Of course, sometimes you will see shielding added, however, not in this case. And basically making them wrap around each other, it's one way of trying to combat the electromagnetic issues that we may experience here. Okay, so in the sense that typically what we are interested here is a differential signal, right? So basically by wrapping them together, we ensure that any interference coming from external will be most likely induced in the same way between both cables. This basically means that the noise will have a significant component that is basically a sum or summary between those cables. So basically we have, the same amount of distortion between the two wires, same, electric field in dust, which means actually if we just take the differential signal, we can simply get rid of the sum signal and part of that interference. And basically the twisting of the cables around each other helps. So it's definitely the better case than putting them just parallel without twisting. However, well, you can see that it's really not great, right? So so still that's not necessarily the best choice. However, what we use very often especially in millimeter wave, in radio frequency is so-called coaxial cable. Okay, so what I told you earlier, here we got the inner metallic core, which is just some wire. We got some dielectric insulator. It's very often this Teflon, can be air. Well, it really depends on the application. Here you can see actually the white part, that's a Teflon. And basically you have the metallic outer shield that can be woven, foil, whatever. However, the outer shield, this is really, will have the negative, well, negative or positive if we think about sign, of course, but it will basically have the opposite sign to the inner shield. Okay, so why do I mention that? Well, there are basically important varies that in the case of the coaxial cable, you can see that the electric field will be built between the center of the metallic core and the outer layer, right? However, all the structure or the signal that we are transmitting, it is fully surrounded by a conductor, by a metallic, right? So in that case, it's actually much more reliant, much more robust to any external influence, right? Simply because we have the signal, the electric field, fully enclosed within our cavity, right? So other important thing is that this is what would be called the unbalanced transmission line. Okay, and the unbalanced, the term basically comes from the fact that the inner dielectric insulator, or the one wire comprising the transmission line, is visibly very different from the other one. So it's not really symmetrical. And if you just handle with wires, this shouldn't make you much of a problem. However, it may create issues when you try to connect your cable to antennas. Simply because with antennas, you also got balanced and unbalanced types of antennas. So we are not going to discuss that within this lecture, but in general speaking, when you connect unbalanced cable like this one to a balanced antenna like the dipole we saw a few lectures ago, which simply consists of the two symmetric wires, that's clearly a balanced antenna type, you need a structure which is called balloon. Okay, so you need a dedicated structure which connects balanced antenna to unbalanced feeding line, or vice versa, of course, balanced feeding line to unbalanced antenna if that's the case. Okay, so with that in mind, I want to move on to the telegrapher's equation. So basically what we want to do here is, we can say, okay, we got the twistor power, we got the coaxial cable, but of course we want to have some mathematical model or engineering description of what to expect from such a transmission line, or how it will work, right? I mean, there's no point of just saying, okay, this is a cable and that's it. So how to describe a cable? And I believe you should have similar with the telegrapher's equation already somewhere in one of the other modules. Well, unless that was before the online teaching. I'm not sure how it works right now. So anyway, the story is that if we take like a dx long, so like an arbitrarily small section of a cable,
Excuse me, you're muted.
okay, sorry, it's okay now. What was the last part I was talking? Or I was
Here
audible?
at the beginning here.
Sorry?
Here, exactly here at the beginning.
Okay.
Yeah, you were muted for like 30 seconds.
Okay, okay. So basically, as I mentioned, if we take like a infinitely, a small section of wire of the cable, it can be modeled using this circuit, right? So the resistor R is the resistance of the copper, or copper. It doesn't have to be copper, right? So anything that the metallic parts of the cable are made of. Now, the inductance L, this might be a little bit more tricky to see where it comes from. However, well, basically, if you think about very thin wire, right? Well, the wire in general will build up some magnetic field around it, as long, of course, as we have a alternating current flowing in that, right? And of course, normally, if we think about classical inductors, we would use some loops of the wire to increase the inductance, right? And that's how the coil works. However, even if the inductance is, even if the wire is straight, it will still generate some inductance simply by the fact that the flowing current will be building, magnetic field and storing energy in the form of magnetic field around the wire, which is pretty much the definition of the inductance, right? So again, per unit, this value might be relatively small, but it still exists. So basically, the L corresponds to the magnetic field that is generated around the current flowing in our wire. Now, if we move on to the capacitance C, well, this is simply the capacitance between the two conductors of the wire. So hopefully, if you take these two metallic surfaces, hopefully it should be clear to you that if you think about the static case, right, there will be certain capacitance built between, we have a metal in the form of a wire, but that doesn't really matter. We have an insulator, And then we have another metal, right? So that's really nothing more than a capacitor, just stretching very, very longly along the cable length. So, and finally, the conductance. This is simply the fact that the dielectric material separating the two conductors is not perfect. So if there are any inaccuracies, there might be some current flowing, between the two conductors. It's usually, again, should be very small, but may happen. All right. So now, again, I put these two characteristic impedances of what cables, and okay. So, sorry, I go one slide back, maybe or two. So, with that regard, if we are dealing with, let's assume the perfect case. So let's assume we have a lossless cable. How we can model that, or which components we would include in modeling of the cable, and which we should remove if we assume cable is not generating any losses. We get four different options. So do you think for a lossless cable we should have a resistance R? Does it stay or does it go? Anybody? Or is it clear what I'm trying to say here? All right. Okay, let's try to make a voting. So we have the four components from our equation, and you can click like next to the components that you believe we have to stick to with our lossless model, and then don't put anything next to the values that you think should be gone, which for the lossless case. And just maybe remind you the circuit, how it looks. Okay, so you think all the four values should be gone, or we have no cable? Or is it,
well, the more natural is the resistance, but actually every component produces the impedance. So there will be losses, I think, for all of them.
Well, actually, not really. So yes, you're right, but that basically that's a good thing. So basically, yes, definitely you're right that R, this is the component corresponding to the losses, right? However, all of them will take into account be included in the inductance, right? However, not all of them are responsible for the losses at least losses in the sense of the, ohmic losses, so attenuation, right? So basically, if you think about the inductor, this is in a principle, again, we're talking about the perfect inductor here, but that's what we're dealing for. So in the case of inductor, there are no losses involved here, really, right? I mean, this is just what it does, that it stores the energy in the form of the magnetic field around it, right? And then, once the current stops flowing, that magnetic energy will be recovered back into the wire in the form of the electric field. So this inductance actually, it's only about energy storage. It does not include losses, okay? Of course, if you think about practical coil, right, it will have inductance together with some resistance, because of the imperfections, right? However, the phenomena of inductance, which is represented basically by this inductor, it's only about storing the energy in the form of magnetic current around your wire, okay? And is that clear? Or is this clear so far or not? Or do you have more? Okay. So, and basically, the same thing when you think about the capacitance, right? This is something which is the opposite of inductance. So in that case, we are storing the electric field energy between the two metallic plates, right? Or within any dielectric that between those two plates, right? But again, the phenomena itself represented by this capacitance, this is also lossless case, because if we switch the current off, or switch the voltage actually of that, to be more precise, then again that capacity will be recovered from the electric field back into the wire, right? And again, even though we have some lossy components in practical capacitors, but that's actually represented by the conductance here. Okay, so basically, for the lossy cable, we have the resistance and the capacitance here. But if we deal with a perfect electric conductor, this R disappears and is replaced simply by a short circuit. And if we have a perfect dielectric without no leakage, this conductance will also disappear and will be replaced simply by an open circuit, right? So basically, we end up with our cable being modeled by a inductor in series and capacitance in parallel, which directly corresponds to the wire, consisting of two different wire or metallization. Is this clear so far?
Yes, it's clear.
Okay, brilliant. Thank you. Right. So we'll skip this slide for the moment, and I move on to the next one, namely the wave impedance. Right. So this is something that I think one of you already mentioned today. And well, typically the impedance is in the form you might be more familiar with. So this is the interpretation used at lower frequencies in classical electronics, that simply the impedance is a ratio between currents and voltages, right? And well, so far so good, as long as the main source of our signal are charges. So charges meaning, electron moving within wire. However, if we move on with radio signals with frequency, we can actually very often deal not with the electrons, but with the electric and magnetic field that is propagating over anything, as a matter of fact. Okay, so even though if you look at high frequency applications, very often you will see wired cable. However, very often a significant fraction of the energy of the signal, it would be actually flowing as an electric current in that copper wire, but it will be actually transmitted by the electromagnetic field built in the dielectric. Okay, so basically this means that you don't necessarily need a conductive, you do need a conductive copper, but the signal is created mainly by the electric field in between the copper rather than flowing through the copper. This got to do with the fact that typically at higher frequency, your electromagnetic signal cannot penetrate very deep into the conductor. So basically you will have some current flowing only on the surface of your conductor, but not through all the volume of the conductor. So that would be the case with lower frequency. Okay, so with that, we have actually a generalized case of the impedance, which is called the wave impedance, which is basically described as a ratio of the electric field to magnetic field. Okay, and so in the general case, it can be expressed using the permittivity and permeability of materials. But at this point, what I wanted to point out is that you can see this actually for the case of currents and the voltages would actually yield, so it would yield the impedance that you're very well familiar with if we are concerning only the movement of charges. Okay, so basically, the electric field, this is more or less corresponding to the voltage at low frequency, and magnetic field that would be also proportional to the current. So this generic wave impedance should yield actually to the impedance that you know well from other modules. Okay, and then basically the calculations comes from the parameters of the material. Okay, so basically, okay, I want to make a long mathematical derivation of this thing, right? However, if you put Maxwell equation, you know that omega mu, that's the parameter, that's the permeability, so parameter corresponding to the magnetic properties of the material. Epsilon here, that's permittivity, so this is of course corresponding to the electric properties of your materials. And here we got like the conductivity sigma. So as I mentioned, at lower frequency, of course, this conductivity will be dominant in establishing the impedance of a wave of a certain medium. At higher frequency, when you think about propagation through dielectric, or in the optical fiber, the conductivity is negligible. And as I mentioned, most of the signal will propagate in the form of electric and magnetic fields. Hence, these two components, permittivity and permeability, will be dominant. Okay. Are there any questions so far? All right. So by the way, what I wanted to point out that also the so-called free space, so the unbounded air, it will also have its own impedance. Okay, so so basically, if you think about the radio signal that is propagating through free space to your mobile or whatever, that signal will also have certain impedance, which, as you might imagine, will be simply dictated by the ratio of the square root of permeability of vacuum divided by permittivity of vacuum. Because again, if you think about radio signal in the air, the conductivity through a vacuum is pretty much negligible, if not none. So again, these two components will dominate, and you can easily calculate that from the constants of mu zero, so permeability of vacuum, and epsilon zero, the permittivity of vacuum. Okay, is that okay? So far, any questions? Okay, it's just that I wanted to make this concept to be quite clear. Okay, so then you can of course use the parameters of the transmission line. So we said that we can approximate a cable using the telegrapher's equation. And of course, we can calculate the line, the impedance using those parameters and using the impedance of the line, right? So this will be basically the square root of the ratio of resistance plus j omega L, where of course omega, that's the frequency, or divided by 2 pi of the signal, and G plus J omega C, where C is the capacitance of your cable. This is well, something I hope you should be familiar. We can also define the propagation constant, which is defined as A plus JB. So one of the components corresponds to losses. The other, okay, so basically there's the real and imaginary components, whereas one corresponds to the losses in the cable, the other does corresponds to the propagation change. And then using our example, right? So if we assume we have a lossless transmission line, right? So we know that the R and the G, they would simply disappear, and we are left with the J omega L divided by J omega C. So basically this, a lossless line can be modeled by the square root of the inductance to capacitance. Okay, and this is something that is well very helpful to us, because of course most of the transmission lines we want to design them as non-lossy line, or to have as little losses as possible, right? So we hope to have the cables or transmission lines which are simply square root of L divided by C. Okay. Now I mentioned to you earlier on that C, the capacitance, can be modeled as simply the area of the between the two wires, right? And then the inductance L, this is basically the magnetic energy stored around the cable while the current is flowing in the cable. Okay, so for example, knowing this, and I'm assuming you are familiar with the the basics of how capacitor works. So let's assume we have a cable with certain that we assume is losses, so we ignore R and G for the moment, and it is filled with a certain dielectric, let's say an R. Now, what will happen to our impedance of that cable if we fill it, let's say, with a Teflon, which got permittivity, I believe, more than double the permittivity of air. So first of all, will that affect our impedance of the transmission line or not? That's the first question. Yes, no. Okay, so to maybe different to break. Let's try to break this problem into smaller steps. Okay, so if you think about the classical capacitor, let's make it a flat capacitor and for simplicity, and you have this certain distance between the two paths of the capacitor, certain area of the paths, and that's not the thing that's changing here. But you got some dielectric in between those paths, right? And how this dielectric influences the capacitance or the electric energy that can be stored with such a capacitor. Any idea?
It increases or decreases the capacitance according to its value.
Exactly, right?
But it's proportional to.
Exactly. Yeah, and that's linear. So I mean, if you double the permittivity, your capacitance how will be affected? So
multiplied by 2 because it's linear.
Exactly. So yes, or generally it will increase, right? So over here, we try to do the same principle, right? So if you have a cable that is filled with air, with permittivity, relative permittivity 1, right? If you replace that air with a Teflon with permittivity 2 point something, I don't remember right now, but that doesn't matter. So if you fill your cable, you increase its capacitance. You probably wouldn't affect the inductance, assuming the material you're filling doesn't change the permeability. So at the end of the day, your C gets so the permittivity of the filling of the cable gets higher. So as a consequence, as you pointed out, the capacitance will also get higher, right? So what will happen of the overall cable impedance? It will, sorry? Yes, exactly, right? Because it's in the denominator, right? And that's more or less how it works. In practical terms, what is important here is the geometry that's in play. And over here, I gave you these two examples of how an impedance of a cable is calculated. And as you can see, those are quite a complicated equations. So, I mean, they won't show up on the exam. It's more to illustrate what parameters are significant, right? So over here, actually, we can see that what we discussed earlier on, the impedance Z0 will be inversely proportional to the square root of the epsilon r. I mean, square root because the square root comes from the capacity, right? But all the rest is actually a complex ratio which comes from the circular shape of the cable, right? Which simply got to do with the fact that the inductance and capacitance will be different based on the shape. Okay, so what is quite important here that for the coaxial cable, we get the impedance of 74 ohms. So 74 ohms or 75 ohms. This is, I believe, the typical impedance that was used for TV cables. So if you got like a good old antenna on the roof, most likely it will be connected using the cable of the impedance of 75 ohms. Nowadays, for most of the devices, somehow we use the 50 ohm standard. So especially when dealing with antennas, or you would basically see that the antenna gets certain input impedance, which is very often, but not always, matched to the 50 ohm standard. And then that, of course, means that you have to also use 50 ohm cable to connect antenna with 50 ohm input impedance. And does anybody know why we need to use the same impedance for the cable and for the antenna? Or in other words, what would have happened if the impedances of the cable and the input impedance of the antenna are different? All right. Well, okay, the answer actually is exactly on this slide. So typically, if we have an electromagnetic wave moving from one boundary to another, well, you should know that if there's a permittivity mismatch, there will be a certain reflections. And the very same phenomena will be actually observed with electronic circuits. I mean, as I tried to explain you already, the Maxwell equations are very generic. So at the end of the day, the phenomena or the principles will be the same regardless of whether it's an optical wave or whether it's an low frequency electronic signals. They can be generalized. So basically, if we have two electromagnetic waves moving from one impedance to another impedance, and those impedances are not the same, part of the signal will be reflected back. Okay, and more or less, this can be calculated quite well using the reflection coefficient. So what we did, we have the reflection coefficient gamma here, and we simply applied this formula. So ZA, this is in that case the load impedance. So A stands from antenna, so this input impedance of an antenna. ZO, this is the impedance of our cable, or can be actually output impedance of a transceiver, whatever you're connecting to our antenna, right? And if they're not the same, well, part of the energy will be reflected back, and we will have firstly less accepted power into the antenna, okay? And secondly, we may also experience what's called a standing wave in our cable, which is also not necessarily a nice thing to have. Okay, so basically the standing wave ratio, or SWR, can be simply calculated directly from the absolute value of the reflection coefficient as calculated here. Okay. So just I wanted to go for a brief example. So this is a case when we are having two cables. One is 50 ohm impedance, the other cable is 75 ohm impedance. Okay, for simplicity, we are talking here about real impedance, just because that's what most cables are characterized. However, of course, in the generic case, this is again can be a complex number, right? So how we calculate this? Well, the equation is straightforward. So we have the ZA minus Z0 divided by ZA plus Z0. So at the end of the day, we have 75 minus 50, which gives 25, 75 plus 50, which is 125. So our reflection coefficient is 0.2, okay, which means basically 20% of the amplitude of the electric signal will not get into the antenna and will be reflected back into your transmitter, right? And this is typically reflecting signal from antenna is, as I said, it's not a good thing. Firstly, because if it doesn't reach antenna, it can be transmitted, so you're being less efficient, right? But the other problem is that the standing wave or the signal reflecting back may actually damage your active components in the transceiver, or drive them actually into nonlinear range, which we'll be talking next week. Okay, so is this concept more or less okay for you, or? Okay, so we'll do just one more example. What I wanted to also point out here is that in the generic case, the reflection coefficient doesn't need to be real. Okay, it can be also a complex number, which is basically expressed here. So, I mean, in this context of the lecture, for simplicity, we deal with the only with real impedance, but that's a very specific case. So in the case of the complex reflection coefficient, well, the amplitude, it corresponds on the power that is being reflected back. However, the phase, so a exponent of j phi that we have over here, this will correspond mainly to the phase change upon reflection. Okay, so this may also happen that the reflected signal will have a little bit different phase. And this we'll actually see here in the two most simple examples. So I guess again, you should be, well, quite familiar with the idea of open and short circuits, right? And well, I'm quite sure you dealt with that quite a lot, okay? So the idea here is that the open and short circuits, they are basically two most extreme cases of the load, or of the that you can be dealing with, right? So let's try to what will happen with the open and short circuits when we apply and try to calculate this reflection coefficient. So in the case of the open circuit, well, the ZA, or the impedance, this can be approximated simply as infinity. So at the end of the day, we have this equation. We have ZA, same equation we saw earlier. Now, this, of course, gives us infinity divided by infinity. So we cannot directly calculate that. That's why I put ZA in front of the bracket so that it cancels out. And then we have like 1 minus 0 divided by 1 plus 0. So at the end of the day, we have a 1 for the open circuit, which means basically, reflection coefficient 1 means basically all of the signal gets reflected back into your transmitter, which I guess shouldn't be that much surprising if you consider that, it's an open circuit. So your signal really, simply doesn't have anywhere to go, right? That's the end of the line. So it gets to the end and bounces back again into the source, into your transmitter. And in that case, of course, you have a perfect standing wave with a node at the end of your wire. Now, how it will look with the short circuit, on the other hand. With short circuit, the impedance is actually 0 because we simply assume, there's like a connection between those 2 points with no resistance. And that changes a little bit our calculation. So, we have ZA minus Z0, 0 minus 50 divided by 0 plus 50. So in that case, we also get the amplitude 1, however, with the minus sign. Okay, and this minus sign, this is exactly what I was trying to tell earlier, that this basically means that there will be like 180 degree of the flip, of the phase flip, upon reflection, right? So it will be still a standing wave, just the phase component will be reversed. All right. So those are the main message here, that even though in both cases we have a total internal reflection, the 1 and -1, this is the difference between open and short circuit, is pretty much the phase of the reflected signal. Is that so far clear? Okay.
So does it mean that for the open circuit we have like 100% of losses because the signal cannot go anywhere?
This is a good question. You see, it doesn't really mean we have 100% of losses. Okay, it really depends how you define losses. That's the point. So because your signal cannot go anywhere, so it will simply get reflected back into your source. Okay. So then what will happen with that signal at the source depends on your architecture, right? But it is not a loss in the sense that, you know, it's not translated into heat. Okay, that's more or less the point of this.
Okay, because in the previous example for the 50 ohms and 75 ohms, we considered this reflection like 20%, yes, because the signal like couldn't go to the antenna.
So yes, so basically so this is right. So this is exactly the same thing. So 20% of the amplitude will be reflected back, right? 80% will enter the antenna, the impedance ZA, and then that part that enters the impedance ZA then will be dissipated. So yeah, I have to be careful what I say here, because of course, if it's antenna, that signal will be radiated, right? But from the circuit point of view, of course, it will be seen as a losses, because suddenly, you know, the 80% of the signal, you know, leaves kind of the system. So that's why we can model this antenna as a resistor, because simply the energy will be dissipated in this resistor, right? Just because we know this corresponds to antenna, it won't be turned into thermic losses as would be with classical resistors, but rather would be radiated. Okay, so that's the thing. Okay.
Okay.
Right. So by the way, it's actually just very good exercise if you are trying to figure out especially certain equation or certain circuit. It's actually always good advice to calculate very simplified case of two extreme cases, and, you know, quickly make a quick calculation how any circuit will behave for that case, just to give you, quick feeling of or intuition of what's happening in any circuit, which is exactly what I did here, right? I took the open and short circuit, which are the two extreme cases. Yeah, and again, like in both cases, we can calculate the standing wave ratio. So we can see this is, you know, infinite because, well, all of the signal gets reflected, so we have a perfect standing wave. So again, the SWR takes only the absolute value of our reflection coefficients, which means if we just calculate SWR, standing wave ratio, open and short circuit would look, you know, pretty much the same for this parameter, just because we lose the phase information about the signal here. Okay, and well, apart from the antenna application, this is also one example of what I consider interesting implementation of this principle is basically what's called time domain reflectometry. Okay, so, and it can be done with both optical fibers and with wires. Of course, in the case of optical fibers, we are sending a light pulse. In the case of the electric wire, we are sending a very short pulse along the cable. Okay, and imagine you have like 100 kilometers of cable that goes from A to B. and suddenly you realize that the cable is broken somewhere, right? So you know it's broken because the information doesn't go from A to B, and you have been tasked with, you know, fixing that cable or making it work. Now, what you would do, of course, if the cable is like, you know, let's say 100 kilometers long, you cannot just, you know, go along the cable and inspect all 100 kilometers of it, right? That's I mean, well, you can, but that's not very efficient way of doing things. So, okay, so probably if you're paid by hours, that may be a good option to get a lot of, you know, working hours with, you know, just walking down the cables and checking them. However, the smart thing to do is that at one option you can connect. Well, there is a specific device basically called. Well, anyway, used for time domain reflectometry. So, okay. So anyway, you connect a source which is able to generate very short pulses. Basically, the shorter the better, because that gives you better accuracy. And you transmit that very short pulse down along your cable. Now, basically, we know from the previous that each discontinuity will reflect portion of the pulse. So if the cable is broken somewhere, regardless whether it's broken because of short circuit or because open or whatever has happened there, it will be seen as a discontinuity. So a portion of your signal, possibly all, if it's a really, you know, short circuit from the broken cable, will be reflected at that point and will go back to your source. So then what you have to do is you measure time between the moment you transmitted your pulse up to the moment you received the reflection. You divide it, of course, by 2, and you apply the propagation speed of the cable, and by that you can say at which kilometer of your cable the problem occurs. Okay, so at which point your cable is broken. So that's basically a smart way of dealing with broken cables. It's pretty much a very same principle as you would see with a radar. The difference, of course, here is that it's easier because you're propagating your signal through a cable and not through an open boundary of a radio signal. Okay, so, and that basically concludes the part of wires, wave impedance, and impedance mismatch. So if you have any questions or... Okay, so if not, I would like to move to another section where we will revisit some old principles that we discussed at the beginning. Okay, so all right. Okay, so now actually I wanted to tell for the next 20 minutes start the topic of amplitude modulation, but this time look into more details how it can be performed or executed and consequences for the spectrum of your signal. So again, well, the Fourier transform, just a quick recap. Basically, as you know, it allows us to move between the time domain and frequency domains. Okay, and so basically, when we have the sine function, it will be seen as a single frequency and single peak, seemingly. However, as you can notice in this diagram, the actually full description of the sine signal requires the presence of a negative frequency minus omega, right? So I think that might be a little bit puzzling in general. So because it's probably easy to imagine, a sine or frequency signal with 1 gigahertz frequency, but what actually does mean a frequency of -1 gigahertz? I mean, if you go back to the core definition of the sine of the frequency, well, you know that 1 gigahertz frequency means simply 10 to the power 9 variations or changes per second, right? So we change the signal quite rapidly over time. But what would that mean if you have -10 to the power 9 variations over second? It's something that might be a bit difficult to imagine. However, the most common interpretation is that this is a form of a mathematical construct. Okay, so obviously you cannot have in real world minus something changes per second. That's it's difficult to imagine. However, those negative frequencies, they are useful for analyzing radio frequency signals, and in a way they occur naturally as the result of the mathematics that we are using. Okay, so there's this distinction here that they are not really physical, but they are a consequence of the math equation that we're using. Okay, and basically there's always some physical explanation for using them. Okay. And that is that our universe, our physics is real. Well, not in the sense of the matrix stuff or lack of thereof, but basically in the sense of most of the signals that we experience over time, they are real valued signals. Okay. However, when we did the Fourier transform, in general, the Fourier spectrum is complex, right? Because we get both the amplitude and the phase of a signal in frequency domain. So seemingly you got one additional dimension in the Fourier transform that you have to account for. And basically the consequence of real valued signal is the fact that we have the conjugated mirror of the positive frequencies. Okay, so as you can see here, that's just a simple baseband pulse or signal actually with 0 frequency, and the bandwidth is W. So the red part are the positive frequency that we normally count. And the blue part, those are the negative frequencies that are, this mathematical construct. Okay, so this comes when you think about it, that if we deal with the exponent of j by phi something, so that would be our spectrum. Sorry, so this exponent value here would be our spectrum here, right? And we often translate that signal as a cosine of phi regarding the second imaginary component that is carried with Euler's equation, with the exponential value of that signal, right? However, in reality, you should know that we should add another component. So if we want to have the real value signal, we actually need to add another complex conjugated component just to cancel out this imaginary part of our signal, right? So so again, anytime we're dealing with real valued signals, we need to have the spectrum which is complex conjugated and basically mirrored with positive and negative frequencies. So just to see how it works, we try to investigate here a single tone analog signal. So again, perfect sine function with just one peak at some arbitrarily selected frequency. And this is modeled here by some amplitude of the signal, which is 2r. It's just a number really. Another cosine of 2 pi frequency of our signal multiplied by time plus some phase shift of our signal theta. And if we move that real signal into frequency domain, what we'll actually get is the superposition. So we get amplitude R. So this is actually half what we're having here. This is the Dirac's delta. So basically, it's like single peak of the frequency at F signal, and also at minus F signal. And then we move on with the exponential value of minus j theta. So basically, this component, the phase shift that comes from this. Okay. So at the end of the day, to see the perfect signal, we need to consider mirrored, complex, and conjugated on the negative frequencies. And as you can see here, one part comes, the phase comes with the minus sign, the other comes with the plus sign. So that's exactly the conjugation. Okay. So is this so far clear? Okay, I hear no more questions. So no, the question is that usually, of course, it's quite convenient to forget about the negative part, because it's just a mirror, and we shouldn't be that much. Usually, we're not that much concerned about this component. However, in modulation, in radio signals, as you will see soon, this is something that actually makes an important difference with our signal. So with that, just a notion about the bandwidth of the signal. So as I mentioned, the bandwidth, this is basically a signal, the width of the signal of the frequency, which contains sufficient number of the signal that we're transmitting. So typically it's defined with 3 decibels below the maximum for analog signals. And typically we measure bandwidth only using the positive part of the frequency spectrum, right? So in the previous case that I showed, when we have the signal starting at 0 frequency, so basically at DC, a direct current, up to a certain value, we'll just count the positive part of that signal. That's the definition of bandwidth. Yeah. So that's exactly here. Now, the problem comes when we, right? So, yeah, and basically, as I mentioned, the amplitude, to be precise, is symmetrical with respect to the direct current. So with respect to the frequency of 0. So basically, yeah, when you have the baseband signal like this, we will measure just the bandwidth from 0 to W. Over here, the signal would be measured sorry. Obviously, you would measure only up to the minus 3 decibels from the top. That's the spectrum that you're concerned. Now, here we move on to the what's called amplitude modulation, but with some more technical details. So what we want to do here is, again, we have the same problem from the lecture 2, that we have a slow changing human speech signal, and we want to encode that into a radio signal that is, let's say 100 megahertz out of convenience. So rapidly changing speed. And how it is done it is basically executed in the process of mixing. Okay, so the mathematical operation corresponding to that is the mathematical operation that corresponds to the amplitude modulation is basically the multiplication of two signals in the time domain. So we have our carrier frequency, which is, let's say, this 100 megahertz signal, and we have our low changing human speech signal. Basically, when we multiply that, we would create a signal at new frequencies that will correspond to the modulated signal that we want to transmit. So just to see how it works, let us assume that we have a signal modulated SM, which is ST. So ST, this is the signal, the slow changing signal. So what we saw are 2r cosine 2 pi f sig time plus theta, the signal, and we multiply that by our carrier frequency, so fc. So this is basically the radio signal, the cosine that we are dealing with. So we end up with this this component here, and in the circuit components, you might experience, this is the device called mixer, which is denoted more or less like this. Okay, so whenever you see in radio circuits this symbol, it basically means multiplication of two different signals, which is, by the way, like a nonlinear operation, simply because it creates, new frequencies at the frequencies that hasn't been there before. So it takes two signals as inputs, multiplies them, and produce the multiplication at an output, which is the modulated signal SM. So in general, to see this, so again, we have the 2R amplitude of the cosine 2 pi f signal t plus theta. That's our signal that we want to modulate, multiplied by the carrier frequency, so the sine of the radio signal of the frequency at which we want to perform the modulation. And just as a reminder, how to multiply sine function and cosine function. So when basically have, like in that case, two cosine function, the multiplication of them can be seen as the cosine of alpha plus beta plus cosine of alpha minus beta divided by 2. Okay, and so in our case, alpha and beta are the two frequencies, right? So what you can see here that we're actually creating a new signal with increased frequency corresponding to the sum of the two signals that enter the mixer. So if we put that in practice, again, this is the same equation. Using the previous equation, we receive amplitude R of the cosine of 2 pi fc minus f signal times, of course, t, and minus the phase component, plus again cosine of 2 pi fc plus f signal t plus t theta. So this is more or less what's happening here. We had our slow changing signal of f at the frequency f sig, and we basically modulated that or moved into a much higher radio frequency that is considered to be that can be basically transmitted over radio, over wire. Okay, is that so far clear? Okay, and nobody pointed actually out that, is this the complete picture? Am I missing something here on this spectrum map? Or so will actually amplitude modulation produce only those two components that we see here? If you go back to the few slides earlier, what I was telling, okay, you have to bear in mind that the even though we change the frequency to a much higher signal, in time domain, this is still a real valued signal because this is just an amplitude modulation. So again, we will have the counterpart of complex conjugated signal at negative frequencies. So as long as we deal with the real signal, this relation has to be there. Okay. So now the question is how to recover the signal. I mean, we made the amplitude modulation. We have this. We created the high frequency signal. We transmitted that over some distance. We use the link budget equation to calculate the received power. Now we want to do the demodulation from the high frequency signal to the lower frequency that we can process in our electronic circuit. So what should we do, or how this can be done? Any ideas?
We should take the envelope of this signal, like coupled, and then somehow extract this in order to have our signal, information signal.
Yes. So I assume by saying the envelope, you mean something like using maybe a diode, right, to directly extract to.
Yes, a rectifier.
Yes. So this could okay. So this could of course work up to certain frequency. However, the problem is that it's not very easy to do if we're thinking about high frequency signals, right? So typically, generally, we want to actually move back from the high frequency back to the baseband frequency, and only then at lower frequency we can effectively use diodes. This basically got to do with the fact that typical diode it's a PN connection, and you might have problems with capacitance at the diode. So anyway, basically the other way of doing that, but in general, what you are suggesting, up to certain frequency, this would work. Above certain frequency, there are technological constraints, simply due to the fact that the rectifier diode is not exactly simple enough to extract all the information. So what we can do instead, we perform exactly the same operation as we started with. So we perform what's called down conversion. So previously with the up conversion, now with the down conversion, by mixing once again with the very same signal of the frequency F carrier. Okay, and then we use low pass filter. So basically how does this work, right? So this is our modulator, this is our channel, and at the moment we are here trying to demodulate. So just to break it down, right? This is our two modulated signal. And then when we multiply our signal once again with 2 pi frequency carrier times t, well, pretty much we apply the same principle. So every frequency at the input will be multiplied by the frequency of FCT. So at the end, we got our F signal, of course, plus and minus, with FC minus FC or minus FC plus FC, plus minus F signal. So F signal is what we're trying to recover, get right? And also at the higher component, we'll have the addition of the two signals. And of course, the negative frequencies. So at the end of the day, we have, we are generated quite a lot of signals. So this is basically combination of all the sum and difference of possible combinations. And of course, we are interested only in our baseband signal because that's like our slowly changing signal that we can process. This is pretty much trash. I mean, we cannot, this is double the original frequency that we are transmitting. So for example, if you think about 900 megahertz of the mobile signal, this would be 1800, which might fall interfere with other communication. So at the end of the day, we would use low pass filter simply to extract only the low frequency components, and the rest just unfortunately goes to the bin, right? So we filter out this very high changing component, but with this you can recover the slowly changing FSIG, and then again you can do further processing at low frequencies by applying the diode and extracting the envelope of your signal from the slow frequency components. Okay, so just to see how it looks formally with the math. So again, we have our modulated signal SMT that arrives receiver. We multiply that with cosine 2 pi f carrier t. So at the end, of course, we end up with our original signal ST that we want to recover times cosinus squared 2 pi FCT, right? And then using the same formula, we end up with half of the amplitude of our original baseband signal plus double the frequency FC, which after filtration, we just got the baseband. Okay. Any questions so far? Okay, so this for the moment. Okay, so we stop here. I think we get a little bit over time, and next week we actually try to continue with some of more analysis of the consequences of this concept of moving between low frequencies and high frequencies. And also we'll take a brief glimpse into a nonlinear circuits that are used for radio transmission, but not only radio transmission, but principally in radio transmission and high frequencies. Also to see how the theory we discussed can be or is actually realized with real electronic equipment. Okay, so again, if there are no more questions, thank you very much for attending the lecture, and that's all for today.
Thank you. Bye.